So let's talk about retail theft. It's way more than a minor issue. We're talking a massive, growing problem. Get this, just last year, losses from theft hit a jaw-dropping $112 billion. And this isn't so slow leak. The cost has basically doubled in just the last few years. In the industry, they call this retail shrink. And the biggest cause, by far? Yep, it's theft. If you look at the breakdown, simple shoplifting, external theft, makes up the biggest chunk. But here's a shocker. Theft by employees is just as costly as theft by customers. It's huge. So who's doing it? Well, it's not just one type of person. It's everyone from pros to thrill seekers. And they're selective too. Certain items, especially small, pricey stuff like accessories, get hit way harder. But now we're seeing a shift from individuals to something much more organized and much more dangerous. And this is a big deal. Over half of all retailers are reporting a major surge in organized theft. Worse yet, things are getting more violent. That puts employees and even customers at very real risk. And don't think this is just a store problem. Nope. The costs eventually get passed on to all of us. What does that mean for you? Higher prices, fewer jobs, and frankly, a much worse shopping experience. So what's the risk for these thieves? Turns out it's low. Like only 1 in 48 actually get caught. With odds that low, isn't any wonder thieves feel so emboldened? It just creates a vicious cycle. All right, so how on earth are retailers supposed to fight back against a problem this big? Well, for years, it was all about those security tags that beep when you walk out the door. But let's be real, that's not cutting it anymore. So now, retailers are turning to much smarter tech. And the new front line in this fight is powered by a real game changer, artificial intelligence, or AI. Think of it like this. AI watches the cameras, spots suspicious behavior, and alerts staff instantly. This is a huge shift. It's about stopping theft before it happens, not just at the exit. So yeah, AI is becoming an absolutely critical tool, and it's completely reshaping retail security. Now, let's delve into the project presentation.
Good morning, everyone. We are here to present our project titled Shoplifting Detection Using Transformers. My name is Ashrith, and I'm presenting along with Rohan and Adwaith. The core idea behind our project is to enhance retail security by enabling CCTV cameras to not just record incidents, but understand actions happening in a store. To explain why this is important, let's look at the context. Retail theft is a persistent challenge worldwide, leading to billions of dollars in losses every year. While CCTV cameras are widely deployed, their effectiveness depends heavily on manual monitoring. Human operators have to watch multiple screens simultaneously, and their attention tends to drop significantly over time. As a result, subtle, suspicious movements often go unnoticed. With advancements in deep learning, especially in sequence understanding models like transformers, we saw an opportunity to enhance CCTV systems. Our objective was to create an automated surveillance pipeline capable of analyzing video sequences, learning motion patterns, and detecting suspicious actions without human intervention. Now that we have the background, let's clearly define the gaps in existing approaches. We identified 4 major challenges. Human fatigue. Security staff lose focus quickly when monitoring multiple screens. Action-based nature of theft. Shoplifting isn't about detecting an object, it's about detecting behaviors. Scalability limitations. It's not feasible to assign multiple staff for every aisle or camera feed. Temporal sequence. Shoplifting unfolds over time, glancing around, grabbing, hiding. A single image cannot capture this pattern. These challenges clearly point to the need for an automated action recognition model. To train such a model, we required a dataset designed for shoplifting behavior. That leads us to the next slide. For our training and evaluation, we used the DCSA-SS shoplifting dataset, which contains a diverse set of videos representing both normal shopping activities and shoplifting scenarios. To ensure balanced learning, we split the dataset into training, validation, and test sets. Each video is converted into 16 uniformly sampled frames, which helps capture key moments without processing unnecessary frames. These frames are then resized to 112 times 112, maintaining a balance between detail and computational efficiency. This process ensures that our model focuses on meaningful motion patterns that are essential for detecting suspicious behavior. Now that the dataset and problem scope are clear, Rohan will walk through our complete model architecture and solution approach.
Thank you, Ashrith. Let me take you through the pipeline we designed for detecting shoplifting. Our approach involves 4 major stages. Stage 1, frame sampling. We extract 16 frames from each video such that they represent the action uniformly across time. Stage 2, spatial feature extraction. Each frame is processed using ResNet-18, which captures visual features such as posture, hand movements, and object interactions. Stage 3, temporal understanding with transformers. This is the core of the model. The transformer encoder examines how movements evolve across the 16 frames, for example, lifting an item, concealing it, or looking around suspiciously. Stage 4, classification. Finally, the condensed representation of the full video is used to classify whether the activity is normal, shopping, or shoplifting. This pipeline gives us both interpretability and accuracy. To understand this pipeline better, let's start with how we extract visual features from each frame. We start with 16 frames, each with 3 channels and a fixed size of 112 × 112. These frames are passed through ResNet-18, which is efficient and widely trusted for feature extraction. The final classification layers of ResNet are removed. We only use the feature maps. Each frame is converted into a 512-dimensional vector, which we then reduce to 256 dimensions, so the transformer can process them efficiently. This gives us a clean sequence of feature embeddings, one for each frame. Once we have these embeddings, we can analyze movement across time. The transformer encoder is responsible for analyzing how actions change over time. It uses self-attention, which allows the model to compare every frame with every other frame. For example, it can detect if someone repeatedly looks around, or if their hand movements are suspicious. Key components include positional encoding to preserve the chronological order of frames, multi-head attention with 4 attention heads for capturing diverse motion cues, 2 encoder layers providing sufficient depth for temporal reasoning, dropout and layer normalization ensuring stable training. After processing the sequence, we use temporal mean pooling to summarize the entire motion pattern into a single vector. This is then passed through a classifier to predict whether shoplifting occurred. With the architecture explained, let's see how it performed.
Our results were very strong. The system consistently identifies shoplifting actions and provides a clear confidence score for each prediction. Here you can see our training graphs. The loss for both training and validation decreases smoothly, showing stable learning, and the accuracy quickly rises to nearly 100%, which means the model generalizes extremely well. The small dip at the end simply indicates the model has already converged. We also visualize the risky frames detected by the model. These red boxes show the exact points in the video where suspicious motion occurs, which proves that our system is not only giving a final label, but also explaining where the model sees shoplifting behavior. Along with this, we built an easy interface where a user can upload a CCTV clip and instantly get a shoplifting prediction. Now, Adwaith will explain the applications, limitations, and future improvements.
Thank you, Rohan. Let me now explain the applications of our system. This model can be used for real-time retail security, where it constantly monitors aisles, smart self-checkout to ensure customers scan purchased items, automated forensic analysis by quickly scanning CCTV footage, smart city surveillance for detecting suspicious behavior in public spaces. Overall, it reduces manual monitoring effort and increases security efficiency. Like any AI system, ours also has some limitations. Our current model has a few limitations. It requires good GPU hardware. It analyzes only 16 frame windows, which may miss very quick or very long actions. Detection may fail if the person is occluded. Accuracy drops if the environment is very different from the training dataset. For future improvements, we plan to optimize for edge devices like NVIDIA Jetson using TensorRT. Add YOLO for item-level understanding. Use pose estimation for privacy-friendly monitoring. Integrate optical flow to capture fine motion patterns. Finally, let me conclude our project. In conclusion, our system successfully combines ResNet 1.8 with transformers to detect shoplifting actions with high accuracy. We demonstrated that analyzing motion over time is far superior to using single images. This solution reduces human workload and makes retail surveillance proactive rather than reactive. Our model is now ready for pilot deployment in real retail environments. I'll move to the last slide. Thank you, sir, for giving us this opportunity. We genuinely learned so much through this project, from researching to building the model to even figuring out how to make proper videos and presentations. This whole journey taught us discipline, teamwork, and how to bring an idea to life. We're really grateful for your guidance and support throughout. Thank you once again.